each corresponding electron and hole be referred to as an electron-hole pair. For example, now, if you be an electron, what do you want for do to fill a hole? And how do you want to fill this hole? By hanging out on the negative terminal as the holes are attracted to you. So this is a fundamental physical property of this drift that is going to take place now. Holes then they constantly drift towards the negative terminal of the voltage source, while electrons flow towards the positive terminal of the same voltage source. The current wey dey flow in a semiconductor na the combination of the movement of both electrons and holes. Now, to be honest with you people, 1 amp of current be equivalent to 1 coulomb per second. That is 1 amp of current be equivalent to 1 coulomb of charge per 1 second. So 1 coulomb per second means 1 amp. This simply means that if 1 coulomb of charge flows through a conductor in 1 second of time, therefore we can say 1 amp of current is said to have passed through the conductor. Now, same here, if we get 6.24 times 10 to the 18 electrons go flow, let's say it go on our right per second, or 6.24 times 10 to the 18 holes go flow on the other direction opposite to the electron when our left per second. Either of them, that's either of these, will be equals to 1 amp. That is the electron hole pair. So now this one, so this one then, these two then, now it make this electron, now it be the electron hole pair. So do not be confused by these holes. I want you to understand the concept of a hole as just the absence of the electron. The amount of current flow in a semiconductor be determined by the number of electron-hole pairs. The ability of a semiconductor for support electric current flow increases with the temperature of the material, because as the temperature rises, the resistance go drop. So that is actually a problem for some electronic systems. Again, because as the temperature increases, all of a sudden, current go want to flow more, maybe more than it was supposed to flow. And this will cause a solid state component to fail or damage. So therefore, solid state material really no go do all this job alone for us. We need to increase the conductivity of the semiconductors, and this is done through a process called doping. Doping na that process of adding specific impurities to semiconductor materials in order to change their behaviors. Now we go really use two different classes of materials as dopants. One of the classes is going to be called a pentavalent dopant, and the other will be called a trivalent dopant. Now, penta means 5, like pentagon. Pentavalent dopant be made of atoms with 5 valence electrons, and the two primary materials that are used in industries are arsenic and antimony. The trivalent dopant get 3 electrons on the valence shell, and this includes indium and gallium. So wetin we see here na a pure silicon in a molten state, and we're gonna add a pinch of arsenic to our silicon, and then we will grow them into a crystalline structure, no longer pure, but now we have a dopant arsenic introduced into it. In doing so, we have just created what is known as the N-type material. The N-type material gets plenty of electrons than holes. Why? Because arsenic na a pentavalent material. That is why the negative charge be the majority carriers. So in the N-type material, as the one we are looking at here, is a series circuit where we get our voltage source here. Now, after applying energy, the electrons are going to flow. That's these free electrons, they go one for flow through the material. And the majority charge carriers here, now these electrons, the way we be grown, during the doping process by adding a pinch of a pentavalent dopant. That's the arsenic material, or the dopant arsenic. And on the same figure, you will see these free electrons then they flow towards the positive terminal as the arrow they show. That's the electrons that they move from the negative to the positive. Since they be the majority charge carrier, they dominate the holes, where they be the minority charge carrier inside the N-type material. The P-type material. The P-type material get more holes than electrons. Why? Because indium na a trivalent material, meaning 3 electrons of the valence shell and with that of silicon. By adding a pinch of indium, when you grow it into a crystalline structure, you will obtain a hole, meaning you grow in an extra hole into the crystalline structure, and by doing so, we are creating this covalent bond. And in this process, we will create what is known as a p-type material. So now the positive charge go be the majority charge carriers. If positive charge is the majority charge carriers, then electrons go be the minority carriers. The holes they always move towards the negative terminals because holes want to be filled by electrons. So in this particular case, that is why both the holes and electrons are going to migrate. So now, for the conclusion under this short introduction to transistors, I say a transistor will help you regulate the flow of current, the pressure, that's voltage. It work like a switch. It also work like an amplifier. We get three pure semiconductor materials where they use them, mostly silicon and germanium. And silicon na the most used semiconductor material so ever. Silicon and arsenic will give you the N-type material, while silicon and indium will give you the P-type material. The N-type material get plenty of electrons than holes, and the P-type material get more holes than electrons. Electrons go always move from negative to positive, while holes will move from the positive to the negative, giving these electron-hole pairs, which mean 1 amp, 1 coulomb of charge per second. So therefore, one of the best reasons of choosing silicon over germanium is its superior thermal stability. Examples of solid-state electronic devices are some things then, like the microprocessor chips, the light-emitting diode lamp, the solar cell, image sensor used in cameras, and semiconductor laser, etc., etc. Therefore, semiconductors are the heart of these technologies and have become the assurance of the digital age.